what is the final temperature when a 3 kilogram gold bar at 99 degrees Celsius is dropped into 0.22 kilograms of water at 25 degrees Celsius? Now, we're looking for the temperature final, the equilibrium temperature of a system. Now, we have a mass of 3 kilograms of gold, so the mass of gold is equal to 3 kilograms. It's at 99 degrees Celsius, so the initial temperature for the gold is 99 degrees Celsius. We always write down our givens. It's dropped into a mass of 0.22 kilograms, so the mass of water is 0.22 kilograms, and the initial temperature of water is 25 degrees Celsius. Now, we need two other things. You need to memorize that the specific heat for water is equal to 4186 joules per kilogram Celsius, and the specific heat for gold is 129. You don't really have to memorize this one. Joules per kilogram Celsius. Now, the gold is being lowered into the water. So the heat lost by the gold is going to be equal to the heat gained by the water. And we'll set up our equation like this. Now, Q is equal to mass times specific heat times the change in temperature. But I like to write the equation like this to let me know that I have to think about whether the change in temperature is going to be positive or negative. So I write it like this: MC plus or minus delta T is equal to MC plus or minus delta T. Because I don't want to write temperature final minus temperature initial in here, because I would have to remember to put a negative sign onto one of these sides later on. So I'll just do that as I'm solving the problem. Let me just go ahead and write mass of AU, AU there, H2O, H2O. Okay, the mass of gold is 3 kilograms. The specific heat for gold is 129. And now I have to think about the change in temperature. On the side, I'll write delta T for gold. Now, the change in temperature, it's going from 99 to some equilibrium temperature. So it's going to lose energy. So 99 minus that temperature is equal to the change in temperature. 99 minus that temperature is equal to the temperature change. Right, the mass of the water is 0.22 kilograms. Specific heat is 4186. And now we have to think about the temperature change. The water is gaining energy, so it's going to go from 25 up to something else. So the temperature change for water, the delta T for water, is going to be that temperature minus 25. So temperature minus 25. And now the only thing I really need to do is solve this. So we throw all these numbers in the calculator and distribute. 3 times 129. It's going to be 387 times 99 minus T is equal to 0.22 times 4186. That gives us 920.92. T minus 25. Now we just distribute. 387 times 99 is 38,313 minus 387T is equal to 920.92T minus 920.92 times 25, which is going to give us 23,023. Now, we have a temperature here, temperature here. We want to get this temperature to this side, move this number to that side so we can solve for T. We end up with negative 387T minus 920.92T is equal to negative 23,023 3,023 minus 38,313. Now, every single term has a negative sign in it, so I can divide every term through by -1 and just cancel out all the negatives. So this becomes positive, that becomes positive, that becomes positive, that becomes positive. All right, now the next step, I can factor out the t here. So this is 387 plus 920.92 equals 23,000. Let me just go ahead and add those together. 23,023 plus 38,313 gives me 61,336. And then t is going to be equal to 61,336 divided by that plus that. So I'll go ahead and just have 387 plus 920.92, and that gets me 1307.92. 61,336 divided by 1307.92 is 46.89. That's degrees Celsius. Now, this means that if you take a 3 kilogram gold bar and you lower it in 0.22 kilograms of water that's at 25 degrees Celsius, the water is going to gain heat energy and move from 25 degrees to 46.89 degrees. Roughly, you can just put 47 degrees. The gold bar is going to lose the amount of energy that the water is going to gain.